Glad to be here today. And I'm going to talk about cloud architecture. And in particular, I'm going to talk about some of the lessons we've learned, which means I'm going to talk about some of our failures. And of course, everybody always wants to tell you how well things are going, but we all know things go wrong. And the most important thing is, what do you learn from it? So a little bit about me, since you have no idea who I am. So I went to NC State. I've grown up in North Carolina. Any Wolfpack fans here? A little bit, yeah, all right, go back. And went to grad school at University of Illinois. Previously worked for SAS and ABB, all here locally, and been at Microsoft since 2003. We have an office here with about 100 engineers who build these two products, Team Foundation Server and Visual Studio Team Services. When I started back in April of 2003, we had a command line spec for a tool that we hadn't even named yet. So I've been in it since the beginning. And now it's a very large product built by folks in Redmond, in North Carolina, and India, so it's a global organization. So mentioning these two products here, let me tell you what they are. So we got our start with Team Foundation Server, which is an on-premises product, and then in 2011 we started building a service, which is Visual Studio Team Services. And to give you an idea of what that is, I'll show you a couple screenshots here. So it is source control, so Git or centralized version control, you choose. Work item tracking, agile planning, so task board, backlogs, bug tracking, that sort of thing. Build automation, and release management. So the entire set of software you need to help execute on a DevOps lifecycle. Now these screenshots are from our actual account, and I'll show you, talk to you about the journey of how we got to where we are. But this is the account that my team uses to build team services. So we build team services with team services. We deploy team services with team services. So I mentioned there are two products, but they're basically the same code base. And I say 90% the same because the things that are different are the things that have to be different in the cloud. And I'll talk to you a little bit about what some of those are. The whole team works in master, and so we're using Git version control now, and that was part of our transformation as we go along this journey here. And so we've got hundreds of engineers around the world, as I mentioned, committing to master every sprint. And a sprint for us is 3 weeks. So in the beginning, we had Team Foundation Server. We had built this on-premises product. We've been building it since 2003. In 2011, we wanted to move to the cloud. And of course, we start, as you would imagine, with one instance, and we just needed to deploy it. So how hard could that be? Well, this is a timeline, and I don't know that you can actually read the timeline here, but that one on the far left is when we shipped the 2010 product, and then 2011 is that next notch. And so we started off, we stood it up for real. Everything's been an upgrade, of course, since then, since you can't reset and lose data. But our deployments were very, very large. And so, since they were months apart, we had to take downtime to do the upgrades because we hadn't done online upgrade at this point. And we had lots of issues after deployment. So we were just learning, trying to figure out how do we make this work and work well. So we get to this deployment in December of 2011. It was terrible. We did the deployment. It took us a couple of weeks to work out all the issues. And we said there's got to be a better way. And so at that point, we decided we would do sprintly deployments. So let's start deploying every 3 weeks. But we needed more than that. So taking a step back, what do we need? So we need more than one instance, because right now everything is global at this point in 2011. We need for us to use it first. And the great thing about building a software for developers and being developers is we can use our own product. And we needed to get to the point that we could use it in the cloud because we were already using it on premises. We need to be able to do online upgrades, and we needed fully automated deployments. Now, when we started, we had deployments that were mostly automated. We had a lot of scripts, but I'll tell you kind of how we went sideways with that. So the first thing I want to talk about here is a little bit of the architecture of TFS and team services. So on this diagram, I call it TFS. There are actually a bunch of services now in team services that actually make up what we refer to as the service, but it's many services. Everything that's been built recently has all been microservices. But when we started, we had this TFS service, and it's got Git, it's got work item tracking, etc. in it. We had a single instance, and the way it's comprised is it's all run on Azure, and so the ATs, application tiers, have the web service endpoints. They serve up the web UI. They are what you connect to from a client, be it Eclipse, Visual Studio, IntelliJ, the browser, etc. The The job agents are also virtual machines running in Azure, and at this point, they're both still platform as a service virtual machines running in the cloud. We are on a path to get to containers next year. We move to containers, but this is where we are right now. The job agents kind of do what you would think. They're running background jobs, so doing things like post-commit processing, build scheduling, cleanup, that sort of stuff. And then we've got a set of databases and blob storage. So the databases, when we started this, of course, coming from this on-premises code base, every customer had its own database by definition in terms of how the product architecture was. So one of the things that we had to do early on was go to a multi-tenant database. So we had literally go add a column to every table, say what customer owned that data to make the database multi-tenant. Because before we did that, and we were already rolling, right? We were actually using this thing as we're building it. We at one point ended up with 11,000 databases in North Central in Azure. This was back in early 2012 before we did the multi-tenant conversion. And then we put files, so be it work item attachments, Git repos, that sort of thing, that all goes into Azure Blob Storage. Whereas on premises, it all goes into SQL. So for things like SQL storage, for authentication and identity, which are different in the cloud, we have plugins for those things. So that way we can keep the same code base, the same team works on both, but it runs in two very different environments. So the next thing we needed to do, I mentioned we had one instance, and one instance, of course, isn't going to cut it. So the first thing we had to do was actually pull out some of the core services out of TFS into a separate standalone service. So account, identity, profile, licensing, the kind of things that everything is going to need as we build out an ecosystem of services. And I mentioned earlier, we need to be able to use it. So one of the early instances we stood up was what we call scale unit 0. And for us, the notion of a scale unit is this set of virtual machines, databases, and blob storage that serve hundreds of thousands of customers. And when an instance gets large enough, we'll seal it off and we'll create a new instance. And so we created SU0 for us. This is where we have our account. And that way we can do interesting things to torture the product and use ourselves as guinea pigs, but not actually inflict it on customers. And then, of course, we started building out across the world. So I show Australia here, we've got Brazil, India, a bunch of different data centers. And of course, Azure itself is adding data centers at a rapid rate. And this allowed us to change our deployment. So the title of the slide is incremental rollout. And once we had multiple scale units, we changed how we do deployments. And so we deploy one scale unit at a time until we get sort of to the end, and then we do multiple scale units all at once. And so with each step of the deployment, we do the deployment, run a health check, wait to see, are there any issues in telemetry, and then you roll to the next. And that way, if a bug does slip through, it doesn't affect the whole world. So as I mentioned, we wanted to be using our own service. We want to be our own best first customer, so to speak. So to do this, we needed to move. We had been using Team Foundation Server for years. We first started using it back in about 2004. We had enough of it working that we had it running on a desktop that was under one of the engineers' desks here in the office in Durham. So long since a lot of time has passed, we had a very nice server running on the Microsoft corporate network, but we needed to move off of that into the cloud. While we were doing that, we said, hey, let's move to Git as well, because we were still using centralized version control at the time. And since we were going to build great tooling for Git, we wanted to use Git. And we also wanted to overhaul our engineering system in general and make the team much more productive. So we did all this in 2014. 2014 was a big year of change, and it started at the beginning of the year with moving the entire system, the entire team into the cloud. So that allows us now to deploy changes to our account first. And whether they're hot fixes or sprintly deployments, whatever change is going out, we do it on our account first. It allows us to aggressively use features as we develop them. And I'll talk a bit about how we control the visibility of the features. And of course, we want to find problems before other people do. And if we're using it, we're beating on it. I've got, again, hundreds of people actively using it every day. That's a lot of load, and I get a great chance to prove it out in the real world. So I mentioned, when we started, we couldn't do upgrade without downtime. Now, when you run a global service, there's no good time to take downtime. It's always crunch time for somebody. So we had to figure that out. And as you saw in the architecture diagram, we've got virtual machines, we've got SQL databases, and we've got blob storage. Can't upgrade everything simultaneously. So something's going to have to be ahead and something's going to have to be behind. Who's going to handle compatibility? And we decided that the application tiers and the job agents would handle compatibility. So the first thing we do when we do a deployment is we deploy new binaries out to the application tiers and to the job agents. They then have in them factory classes where they reach out, they know what version of the database that they're talking to, and they load the right class to talk to it. And then at some point, those binaries will initiate the upgrade of the databases, and then of course they'll have to switch and load a different class. But this allows us to have all that logic in our case, C#, could be Java or any other language. And those of you who've written SQL know SQL with a bunch of if statements is a bad thing. So it allowed us to keep that complexity out of SQL and make it easier for us to test. And of course, as I mentioned here, roll back if needed. So how do you do a database schema upgrade online? Let's talk about that for a little bit. If you're going to hold a lock, you can't hold a lock very long. Because if I hold a lock long enough that you can't use the product, I took you down. It doesn't matter what I call it, right? So the first phase that we go through is we go through and manipulate data, change the data however we need to ahead of the actual upgrade phase. And for some teams, they'll choose to do this a sprint ahead. Let's say you're going to add a new feature. Let's say you're going to track new data about your builds or about Git. Let's say we're adding a feature to do that. We'll go ahead and add nullable columns and run a job on the job agents in the background to populate that data and maybe install a SQL trigger to keep it up to date. And that way then, when we get ready to do the actual upgrade, the data transformations have already been done in the background and therefore don't interfere with how long it takes to run. So then we go into a deployment mode in the applications and the job agents, and we can go to phase 2. And phase 2 is pretty simple. Each of the job agents in the application tiers, when they're in this mode, they grab what we call a reader lock. And of course, it runs stored procedures, so they're actually modifying things, so it's a bit of a misnomer, but grab a reader lock. Meanwhile, the deployment is trying to grab the writer lock. And what you as a user should experience is, maybe you're trying to save a work item, and instead of taking a second to save a work item, maybe it takes 5 seconds. And then the system goes back to normal. You never notice. You don't lose work. You know, the comments that you typed in your bug are still there. And the upgrade happens, and you never realize it. And in fact, if you don't click the mouse at the right time, you wouldn't even experience the delay. So under that lock that we take, we're just manipulating the metadata. So we're going to change stored procedures, we're going to change indexes, whatever it is we need to do. But we do it behind the scenes, everything's completely online for you, and you never have any idea that anything happened. The other thing too, by the way, to pull that off, is we also version our web UI. So the JavaScript files, the HTML, the images, everything gets versioned, because if you're using the interface, and of course most of it is sort of a single page application architecture, and until you hit refresh or do something that causes a refresh, you're still using the old file. So we want it to be completely seamless. You never know. So talking about deployment. Now deployment is interesting. When we started, it was much smaller. There were fewer people working on it. It's a smaller service, and you've got scripts to do the deployment, but it's easy to get tempted to go, hey, can you just run this for me? It's a one-time change I need to make for this deployment. And so commands would start floating around in email. And somebody said, hey, let's formalize this. Let's put it in OneNote. And so people are emailing things around like this. Hey, could you run this command for me during upgrade? And it doesn't matter what it is. Let's say this is a PowerShell script, set options, some text. What's wrong with this? Well, those quotation marks there, OneNote, Word, email, they all like to change them into fancy quotation marks for you. Those don't work on the command line, of course. So what had happened was, over time, people had started to take shortcuts, right? So everything's supposed to be scripted, but these one-time things. And somebody was literally running these commands, trying to do the deployment. So of course, we get to some deployment where somebody misses a step. Halfway through, they missed a step. You get all the way to the end, nothing's failing. We try to use the service, it doesn't work. Because this is back in 2013. We still got a single instance. Thankfully, this was pre-production. This didn't happen on live site. But at that point, it was clear you can't be almost automated. Anything that you've got that's not automated, that you're relying on a human to do, is just an opportunity for failure. So I said, okay, we've got to be fully automated. We have an event coming up that fall. We can't have any of these sort of one-time commands that get run manually. So everything has to be checked in. All your scripts, everything has to be in version control, fully versioned, and that way every deployment you do is the same, whether it's pre-production, whether it's production. And these days, as we added scale units and started to grow out, of course, you've got a scale problem anyway. If you've got anything you've got to do manually, now we've got probably 40 scale units of different services running around. It becomes quickly untenable. So additionally, as we added all these scale units, we needed something that would orchestrate the overall process. We built a release management feature, and as I mentioned earlier, we actually deploy team services with release management. So given that, we've got a much better deployment now. The whole team's working in master. So how do we control what features show up? So this is a product, and there are times when you want features to show up because you're done with them and you're ready for the world to get them, but maybe you're still developing it. How do you control that? So we started with a notion called feature flags. We didn't invent it. I know Facebook's done it for years. They probably weren't the first either. But we've got code here. So your mainline code is running, and you start adding a new branch to the code to generate a new feature. And I'm actually going to show you one here in a minute. So let's say I add a new feature. Let's say I'm adding a new button to the UI, but I only want that to show up for certain people. So I put it behind a feature flag. And that way I can start progressively displaying that button to different people. So that way, for example, we can start dogfooding it ourselves or using it ourselves. So we deployed our accounts first. We can start turning it on for us. We turn it on for our personal accounts. We turn it on for select customers who've opted in to kind of be on the bleeding edge. And then as we're happy with it, and after getting feedback, doing some experimentation, etc., we can now turn it on and have the entire world go through this new code path. Everybody's got a feature. Then we can go back and delete the old code, delete the old feature flag, and now this is the normal path for the code. So why do feature flags? They allow us to decouple deployment and exposure, meaning I can do the engineering work whenever it works well for the team, but I can expose it when the feature is done, or maybe for a conference or other event. We've got control down to the end user. We can change it globally. We can change it for a user and everything in between. All these changes can happen without any kind of redeployment, so no need to disturb the service or take any risk in terms of downtime, etc. And it's controlled via PowerShell or Web UI. In other words, it's scriptable, and you can also do it interactively. And again, as I mentioned, we can do experiments. We can get feedback. We can have some of these customers I mentioned earlier that have opted into this give us feedback on, did we get the feature right? One of the biggest features we did under a feature flag lately was pull requests. We already had pull requests for Git, but we completely overhauled the Web UI. So we had two versions of the pull request feature running simultaneously on the service. Most people were getting the old one, and we progressively pulled in more and more people to the new one until we got rid of the old one and everyone gets the new one. It worked very, very well. It also gives us a quick off switch. So some teams, when they add new features, they add the ability, they add them under a feature flag, because then if you need to turn it off for some reason, maybe something goes wrong or you have some other issue, it becomes a very easy way to turn that off without any kind of deployment or rollback. So I'll give you a quick example. I showed you some screenshots earlier. This is a screenshot here of a pull request, and this is a new feature, a revert button, make it easy to roll back and change in Git. This feature is actually not on the public site right now, but it is under a feature flag. And so let's take a look at what it takes to define a feature flag. So this one, since this is a revert button, it's called source control.revert. So we literally have a XML file. In fact, there are multiple XML files per service where you can define your feature flags, and it's literally just a line in a file. The infrastructure takes that, creates the database entries, manages the lifetime of that feature flag. So I, as an engineer, I add a feature flag for my source control revert button. And then in the code, and this is the actual code off the website, it's written in TypeScript, which compiles into JavaScript. And all I have to do is I have to check, is that flag on? And if that flag's on, great, create that revert button. And as I mentioned, you can do it from scripting. In the case of PowerShell, get feature flag, set feature flag, you can manipulate it from any kind of, from your scripting environment. But you can also do it interactively. This is an internal tool that we built to be able to control feature flags. And what I'm showing here is, for this one, I went and queried production right now, did this a couple days ago, And one of my personal accounts has this flag turned on, and that's where I grabbed the screenshot. And the other personal account of mine does not have it turned on. So it's only on for a small number of people right now. So feature flags sound like a great idea. I can control when a feature is available, but what could go wrong with that? Well, we had this event in 2013. It was in November 2013. It was in New York. And part of the event was to unveil a bunch of new features that we had put together in team services. Well, we had the brilliant idea that we're going to turn on the features right before the keynote. And it sounds like a great idea, right? Back at this point in time, because again, this is several years back, we still only had one instance. So we're going to turn on a bunch of features right before a keynote on the only instance we have in the world. It didn't go well. When we did this, we flipped them on about 9:30 that morning. There was a keynote at 10 a.m. My boss, Brian Berry, who's originally going to give this talk, is on the phone, asked me what's going on. And we're trying to sort out what went wrong. Now we started turning feature flags off and kind of get the service sort of limping along to kind of get back to a healthier state. But it took us literally a week to work through it all. Now, this screenshot is actually from a blog post that Brian wrote. One of the things we try to do with every problem we have is do a thorough root cause analysis. Some of you probably heard of the 5 whys. Keep asking why till you get to the real root cause of what the problem is. We value transparency quite a bit. So Brian's actually written blog posts. If you want to go back and look at some of the lessons we've learned the hard way, he's got blog posts and he'll post the RCAs. Those RCAs are the same as the internal RCAs that we write, except they give you a little more context about what's going on. They don't assume as much knowledge. But it's otherwise exactly what the root cause was. So what did go wrong? So clearly we turned it on the morning of the event. That was a bad idea on the only instance we had at the time. So what do we do now? Now we have multiple instances. As I mentioned, we can roll things out incrementally. We can also make sure we turn on feature flags at least 24 hours ahead of an event. Now, there's always the possibility of something leaking, and sometimes there are some tweaks you can do to kind of hide things, make it harder to find the entry point, but we otherwise want it running in production. And the exact opposite thing happened in November, again at the Connect event, November last year, November 2015. We rolled out a brand new marketplace for extensions for team services, and that went beautifully well. And we turned on the feature flags for that, had everything going in production, had certain select customers trying it, 2 days before the event. The event went off without a hitch. It was we had clearly learned our lessons well from 2 years before in that 2013 event. So how do we control feature flags? So we have a process we call stages. And so we have stage 0, which is us. We have a stage 1, which is our personal account. Stage 2, which brings in some select customers, etc. And by having a standard set of stages, everybody who develops a feature under a feature flag can go through and opt in the same set of customers. And so it becomes a very predictable process to do this. Now, as I said earlier too, of course, you can do something through the web UI if you're doing something kind of one-off. So for example, we rolled out SSH as a feature. When we did that, I actually wrote a blog post that said, hey, if you want SSH turned on your account, let me know. Because it's not a feature that every single person is going to use. We wanted to get more users and ask people when they send me email. I could enter that into the website. Actually, I had the version control team do that, but it worked really well. So in that case, I can turn it on for an individual user. I can turn it on for an account. I can turn it on for a scale unit. I can turn it on globally. So I have full control over what I do with it. And of course, the next thing that's key is that you monitor it, right? You're going to turn this feature on. You got to have the right telemetry in place to understand did something go wrong, and if it did, revert, turn it off. So I just talked about a case of failure. Failure is going to happen in the cloud. If I can't prevent it, what can I do to limit the impact? So let's take a look at another example of a lesson we learned and what we've done about it. So in the Visual Studio 2013 product, we introduced a new feature called synchronized settings. And so you can run Visual Studio on 2 or 3 boxes. Let's say your laptop and your desktop, and you want your theme and other things to synchronize across them. So we launched this feature, and the way it worked is the settings would get synchronized in the background. And you remember Shared Platform Services from the architecture diagram, SPS, which has authentication, licensing, all these key features. And Visual Studio is establishing a connection to SPS and asking for notifications. Let me know when settings have changed. So this graph here, when we set up that connection for notifications, it's normally extremely fast. This graph shows 5 days of what that time looks like. There's 1 day here that goes through the roof. And it's so out of scale that all the others look flat, like it takes 0 time. So creating a subscription slows way down, and we have a major problem. Let's look at what happens here. So VS requests notifications from SPS. SPS says, hey, I'm going to create a subscription in Service Bus and hook up that push notification so that the service can tell VS, hey, another instance of VS has changed settings, you need to refresh. Creating that subscription is normally fast, but it's slowed down. SPS, the way the code actually worked is it would grab a thread on the thread pool, create the subscription, and you can now start to see where this is going to head. The thread pool was quickly exhausted because it took too long to create the subscription. The thread pool is finite, and pretty soon we're in trouble. Requests start queuing, nothing else can run inside of SPS, which of course is this critical service that had auth and so forth, and it took site down. To compound that, Visual Studio had retries. It would try to create this connection. This connection was failing, or timing out to be more precise because of the slowdown. SPS would retry the connection to create the subscriptions in Service Bus when that was slow. So on top of the timeout issues, everything's trying to redo this over and over again, executing retry logic. That made it even worse. So what do we need? What are our goals here? We need something that will allow us to limit the impact of a problem. Here it is, we have this feature, synchronized settings. It's trying to connect and use SPS. We had a bug, and instead of just taking out the synchronized settings feature, it took down the service. We need to be able to degrade gracefully. Let's imagine it's not working. Well, if your settings don't synchronize for the next half hour, is it really that big a deal? Of course not. And we also want it such that when the issue is gone, the service recovers quickly. So for this incident, we mitigated it by turning off the feature flag. The other thing too, by the way, that we've done since then, is we've actually factored this service, broken the service apart, and this code now runs in its own service with other also less critical items in it. So, but could we detect when this dependency, in this case Service Bus, could we have detected that Service Bus became unhealthy, that we're starting to hit timeouts and fail fast and recover in a better way? So we started looking around. We found this thing called circuit breakers, and this originated at Netflix. I'm not going to really do it justice in the time that I have today. There's a lot of information. We'll talk a little bit about how it works, but if you're interested in circuit breakers, I highly recommend looking at the Netflix presentations. They go into it in great depth. But it started at Netflix, and what it is with electrical connection, electrical circuit breaker, of course, the circuit's normally closed, current is flowing, and then if the current exceeds the rated capacity of the circuit breaker, it opens up and stops the flow of current, presumably to stop further damage to the equipment. So we want to do the same sort of thing, but in software. We want to stop failures from cascading across the system and having impact beyond where they originated. And we really need to protect from 3 things: latency, or being slow, failing, and volume. Now, latency is actually worse than failing. If my service makes a call to another service and it fails fast, I can decide what to do about that. But if I make a call and the timeout is 30 seconds or a minute or 5 minutes, well, now everything slows way down. So the timeouts become very, very important, the amount of latency there. Another, of course, is volume. Let's say the system's working like normal, but we just simply get too much volume to handle. What do we do about that? So we want to be able to shed that load quickly and recover. I want to be able to fail fast. But I also need some sort of fallback mechanism. Great, there's a failure, I contain it. What do I do if I can't do what the user asked for? So let's take a quick look at a circuit breaker transition diagram. It's a little harder to read than I had anticipated, but it's a very simplified version of what goes on in the circuit breaker. So normally it's closed. The command comes in, we're going to run it. If that command fails or succeeds, either way, we're going to record that information. And we're going to keep a rolling window of time in little buckets. In this case, let's say it's a second, and I'm going to look at a 10-second window, and I'm going to see what percentage of these requests are succeeding or failing. And if too many requests start failing, I'm going to open up the circuit breaker. I'm going to stop taking requests essentially and fail them. But in order to recover, I need something that tells me, is that dependency okay? So I'm going to let some of the requests go through. And if enough requests are succeeding, I'm going to reclose the circuit breaker and go back to normal. So what does it actually look like to use a circuit breaker? So this slide's an eye chart, but you don't really need to read but a couple of things here. I've got a set of settings that I can control a circuit breaker with. I can pick what the volume should be. So one of the interesting challenges is if I have something that doesn't get called very often, how do I know when to open or close it? So if the volume's high enough and the error rate is high enough, here the code says 50% error rate, then I want to open it. And as I mentioned before, we're collecting statistics. So over what time? And this says 10 seconds. Collect statistics for the next 10 seconds. So in the code, it becomes very easy to use this. So whereas this particular code wants to make a call to fetch the extensions that are installed in somebody's account for team services. Normally it'd be a one line, I just call and get that set of extensions. Here I wrap it in a command service class. The run method is call what I actually really want, fetch installed services. If that starts failing and the circuit breaker opens, I've got a fallback here. And I call the fallback, and that would give me a default set of extensions. So I, as a user, if something goes wrong, I can still get access to all of my code, my work items, et cetera, et cetera. It's all still there. But I may lose maybe some functionality elsewhere, or maybe I get extra functionality. It's one of the things we look at when something goes wrong, if you're going to fall back. Give people more, not less, right? The other thing that's interesting here is at the top line, we give it a name. So we give every circuit breaker a name, and that way in the telemetry, we can actually see what's going on and correlate that back to the code. The other thing I mentioned was volume. And so one of the things we want to do is limit concurrency. How many simultaneous calls can I make before things go wrong? So by implementing limits, I can prevent an overwhelming number of requests taking down some particular resource. And that also gives me the opportunity, of course, to fall back gracefully. Now, an example here would be a database. And in our case, we limit our databases to 100 simultaneous connections. So let's look at a different event. This time, it happened last month. There was a database that slowed down in shared platform services. Doesn't matter why, but it got slow. It was slow for a couple of minutes. And since we have a circuit breaker now in the code, and the circuit breaker limited to 100 connections, when whatever was going on slowed down, as soon as we started getting more than 100 requests that would have otherwise opened connections to the database, we start shedding them, we start failing them. And this graph here peaks at just over 90. And so for a couple of minutes, there were too many requests. Once we hit 100, we let those go through. Anything above that, we failed it. Went to the fallback, whatever the fallback was for this piece of code. And so the great thing is, it wasn't an emergency. Nobody got called. The on-call engineer didn't have to do anything. Some set of users got degraded functionality, but the service remained healthy. So, great. I go add circuit breakers to my code. I make it more resilient. How do I actually know that it works? And that's where fault injection testing comes in. And this is the goal here is to inject failure intentionally to see what happens on the system. And again, our own personal account, our own team account, being in scale unit 0 to scale unit that's just us, comes in really, really handy. So we can go torture our own team, so to speak. We can torture the system and not affect customers and see, did we get resiliency? Did we get our circuit breakers correct? So we achieve resiliency. Now, one of the things that we like to go do is go back in history and look at some of our past lifecycle incidents and go simulate those, go try those out. We'll also just randomly fail things. And this is something, I mentioned this idea came from Netflix. They have become very, very mature at this. They do this in production all the time. They introduce failures and monitor to see is the system sufficiently resilient. So we can put in network problems, we can slow down the network, we can introduce just connectivity problems, and we can also just randomly open circuit breakers. And what we're looking for here is, does the service fail gracefully? Do we handle it appropriately? Do we get the expected fallback that we thought we should? And when the event is over, do we recover gracefully? Now, that turns out to be really important, because the other problem that we had when we hit some of these failure modes in the past was, I mentioned the earlier event where the requests would start queuing up. Well, if we overwhelmed a SQL database and there was a problem, As soon as we fixed the problem and the SQL database became healthy again, that queue of 1,000 requests or whatever it was would just immediately slam the database and take it back down again. And so you get into this very bit of a death spiral there where you're constantly overloading the system again. And it's important to get rid of those queued requests to let the healthy system function properly. So I'm going to go through one more thing here. And this time I'm going to make a config change. And let's look at what happens, because this is another live site incident. And let's see what we learned from it. So this happened February 4th of this year. It was at 9 a.m. UTC. It's 5 a.m. Here in North Carolina. The service looks healthy, looks normal, everything's good. And then the developers in Europe start coming in to work, and stuff starts going wrong. So here, the code is trying to authenticate and grab a token, again from SPS. Alerts start firing as the errors start spiking. The on-call engineer gets woken up, starts to diagnose the problem. This problem turns out to be a very hard problem. We pull in a number of other people, including some of our best SQL developers, to figure this out. We actually got help from the SQL team itself, because this one turned out to be rather hard to diagnose. And what we started to see was that there was a SQL procedure that was causing a huge backup, a huge backlog of queries. Why is that? So SQL has this notion of compat level for what's called the query optimizer. So you write some SQL, the query optimizer tries to figure out what's the best way to run that code. And every release of SQL, that query optimizer will change, but they allow you to pin it to whatever version you've tuned your code for. And so we had previously been using the 2008 compat level. We had most of our DBs switched over, so we were going to switch everything over to 120, which is the equivalent of SQL Server 2014. Well, it turns out there was a bug there, and the cardinality estimator in the query optimizer decided that for a query that normally returned only a row or two, a small amount of data, suddenly needed 3.5 gigabytes of RAM to run. The machine only has 48 gigabytes of RAM. It didn't take long to completely overwhelm it. Now, this blue circle here in that text you probably can't read says resource semaphore 99.56%. We were sitting there waiting almost 100% of the time. So we're in a bad state. So here's the code that went wrong. And I could ask you, do you see a problem with it? And it's a trick question. There's actually nothing wrong with the code. It was a bug in this optimizer. And the code is actually well tuned for scale. This is a table with millions of rows in it. It's got hints to force a good, healthy query plan, yet this went terribly south. Before we made this change, I mentioned we had pinned it to the equivalent of SQL Server 2008. This is what it looks like when it's healthy. That blue is executing code. The amount of waiting that's happening here is only a few %. So this is healthy, and what it looked like ahead of the change. So during the incident, of course, you just want to recover. You just want to get the service back to a healthy state. How do we do that? Here we added a hack in the code. We said, hey, we're gonna pin it so that this query can't take more than 1% around. And it turns out that was enough to get the service back up and running. And once we made that change, things go back to normal, and we now need to go work on the real fix. So what was the root cause? The root cause here was there was a compatibility bug, an issue in the query optimizer here that was triggered when we changed compat level. Now, most of our databases had already been set to 120. We were just setting the rest of them to 120 so that we get it uniform. Because as many of you know, when things are different, that's often when problems occur. Because if somebody's got to remember, oh, this one's this way and this other one's a different way, you're just begging for problems. So uniformity is best. And we thought, since we had done this elsewhere, we had done enough testing on it. So we had one of the last DBs to be changed was this global identity DB. Circuit breakers, which I just went through, are great, but here's an interesting case where it affected a particular stored procedure. Everything slowed down. Circuit breakers are great in the way we've set them up to be able to disconnect calls to a single database, but they're not per individual stored procedure. And even if they are, you then have to figure out which one's the slow one. And when everything slows down, they all look bad. So, but really the root cause here is we have this remaining DB here that's a single point of failure. And we're in the process now of finishing up partitioning that particular DB and the service associated with it. But what's interesting here is, I told you we'd made this change earlier. We didn't make the change the day before the event started. We actually made the change 2 weeks ahead of time. So the next thing we're trying to figure out, and this is kind of where we're going next, so there's not a conclusion to this part of the story, is could we have detected this earlier? So this update happened on the far left there. There's a little blue spike. That's the first time, looking back in the telemetry after the event happened, that we start to see the amount of memory requested by SQL start to spike. The day before it took us down, it was the biggest spike we had seen. Again, looking in hindsight, right? We didn't see this ahead of time. But that actually exhibited itself in an issue we had the day before, but we didn't go look at it, which was a mistake. It was something that had happened, but people were tired. We didn't go fully figure it out then. The next day, the amount of SQL memory requested, and if you could actually read the numbers on the left, you would see that it actually exceeded memory in the machine, and that's the point when it all went south. Now, we have all this data because we take, there's a feature called Query Data Store in SQL Azure. We take the query plan data, all the information that SQL Azure will give us, we shove it into our telemetry system so that we can go back and do this kind of analysis. So we've got an immense amount of telemetry. Anybody who runs a cloud service, you've got telemetry coming out your ears. How do you make sense of that data sooner? And so the question we're asking ourselves is, could we have spotted that problem starting 2 weeks ago and have fixed it before it ever affected anybody? And this is something that we've called anomaly detection. Now, in an ideal world, we'd apply artificial intelligence, machine learning to this and come out the other end with an awesome solution. We all know in reality it takes a lot of tuning, because if you're not careful, you'll just bury yourself in false alerts. So we started experimenting with what we call high maturity monitors, and basically we have these queries that run against the production telemetry that are supposed to return 0 errors. They're 0 results. They're looking for something being wrong. So we're just starting down this road. So I don't have a great story yet to tell you of, yes, and we did this, and here's how it turned out. And it's not a silver bullet. You'll never be able to spot everything. But this is one of the next things we're going to do on our journey. So to wrap up here, we started in a world where we had an on-premises product. We moved it into the cloud. We're rapidly building the product and shipping it both on-premises and the cloud, all at the same time. Very much an evolutionary journey here. So we got to a healthy deployment state with incremental and online deployments. We have the ability to apply production load to every change because we use the product ourselves and are able to experiment and make sure the product is good before it goes to customers. We have feature flags to control when our features show up and who gets access to them. We've introduced circuit breakers, and I'm happy to say there are many instances I could go through where circuit breakers kicked in, they did the right thing, and very few people ever noticed. And of course, partition everything. Starting as we did from an on-premises product, we started from a single instance, and it's been a progression to split it all apart and introduce the redundancy that we need in order to achieve high availability. And the last thing we're starting to look at is, how do we detect these problems early? If something starts going wrong, how do we see it before it happens or becomes a problem for customers? So thank you very much. Here's my contact information. You can find me on Twitter easily enough. And if you have any questions, stop by outside, and I'd be happy to chat with you. Thank you very much.